P is less than 900, what you have is that negative P of t minus 900 equals CE of t. Right? That's to say, P of t minus 900 equals negative C e to the 1/2 t. Okay, but in either case, P of t is going to be some constant, right? Some constant times e to the 1/2 t plus 900. Right? Right? In either case, this is what's going to look like. P of t is a to the 1/2 t plus 900, right? P of t is going to be 900 plus some constant times e to the 1/2 t. P of t equals some constant times is 900 plus some constant times e to the 1/2 t. Right? Everyone following? Everyone following? Okay, good. Okay. So this is what happens to the mouse to the mouse population, right? To the mouse civilization, right? Right. And so let's ask, what if at time 0 the mouse population is less than 900? What if at time 0 the mouse population is less than 900? Okay. So okay. So P of t is A of t. A e to the 1/2 t plus 900. Okay. So if P of 0, so let's think about P of 0. Okay. Think about P of 0. P of 0 at t equals 0. P of 0 is a to the 0 times e to the 0, that's 1, plus 900. Okay, so what's A? What's A? What's A? A is going to be P of 0 minus 900, right? The population at time 0 minus 900. Population at t equals 0 minus 900. Okay, so now let's imagine some scenarios. Suppose the initial population is smaller than 900. Suppose the initial population is smaller than 900, then A is negative, right? A is negative. What happens to the mouse population? It's decreasing, and they will die off within a couple, they'll die off really fast, right? You know that P of t equals A is 900 plus A e to the 1/2 t, but A is negative, right? And soon the mouse population is over, right? The mouse, that's the end of the mouse civilization. Okay. But if the initial population is bigger than 900, what happens? There's an increase, right? Then, this is less than 0. P of t is 900 plus a e to the 1/2 t, and a is positive, right? And the mouse population overwhelms the entire world eventually, right? Okay, this is kind of interesting. So there, in this situation, there's sort of a critical population, right? Oh, and what if the population is 900, perfectly 900? It'd be stable, right? The mouse population stays at 900 until the end of time. Okay. So this is this funny thing that happens, right? There's this equilibrium point. So 900, and this is sort of like equilibrium, right? The population is growing, but it's being killed off at the same rate that it's growing, right? If you have more than 900, then that's good. The population is increasing, is growing, and you're being killed off, but not as fast, right? So you're going to overwhelm the world, right? If there's less than 900, your population doesn't increase fast enough, and everybody is gone. Maybe this is something about the human. This is the future of the human species as well. No, it's not. It's not. This is who's killing us off. I guess people are dying. Anyway. Okay, so I hope you get some sense of differential equations, right? It's kind of cool. You separate the variables, and then you get some information about how your function behaves. Okay. So. So, going back to the prototypical equation. Back to the prototypical equation. Remember that was p of t turned out to be some constant e to the kt, right? Okay. So, in fact, in the world, there are a lot of things that behave like this. So in the real world, many phenomena follow this behavior. Huh? I'll ask later. Okay. Many phenomena follow this behavior. One is money. Okay. One is money. If you put money in a bank, money grows following this behavior. Okay. If you have an interest rate, so like C of t, a naught e to the rt. So a naught is your initial amount. R is your annual interest rate. And T is your time in years. Okay. Then money actually, money in the bank, that's what interest is. That's what interest is. Money will grow at an exponential rate. Okay. So, if you invest money, that's good, right? Start investing at an early age. It will grow exponentially, right? Don't wait until you're, if you invest your money early, it will have a long time to increase. Oh, cool. Thank you. Okay. Another thing, radioactive material. So if you collect radioactive material, I'm afraid it will decrease at an exponential rate. Okay. So the amount of material you'll have will actually, there will be some sort of decrease, a rate of decrease, and it will decrease at an exponential rate. Number 3, there's something called Newton's law of cooling or heating. So Newton's law tells you that if let T times T be the temperature of an object, okay, and let TA be the temperature of the room, so-called ambient temperature. Okay, the ambient temperature, the temperature around you. Okay. It turns out that the rate of change of T is proportional to the difference between the temperature and the ambient temperature. Between the temperature and the ambient temperature. In other words, if you have a piece of ice in a really hot room, the rate of change of its temperature will be fast, right? It's proportional to the difference between the temperature of your object and the temperature of the room, right? If the temperature of the room is very close to the temperature of your object, then the rate of change is slow. Okay, that makes sense, right? If the room is hot, your object is going to warm up quickly. If the room is much hotter than your object is going to warm up quickly. If the room is just a little bit hotter, your object is going to warm up more slowly. Okay, so right. So notice that this is the same thing as saying that d dt t minus ta equals k t minus ta. Right. And so we're again in a situation where the derivative of something is proportional to that something. The derivative of that something is proportional to that something. Right? The derivative of something is proportional to that something. Right? This is our f. Okay, and so we're back in the prototypical case. Right? And so what we get is that the function equals some constant times e to the negative kt. So all of these things behave like that first example. All of these things behave like the first example, right? A naught times e to the RT, right? Something times e to the some constant times t. Okay. Okay. So because they all follow this rule, we can answer questions by using this information. We can use this to answer questions. So let me give an example. Okay. So here's some examples. One, the radioactive element polonium has a half-life of 139 days. Okay, so what that means is that if you start off with a certain amount, in 139 days, it will become half, right? Because the radioactive decay, right, becomes half of what you started off with. So what does this tell us? This tells us that at time 139, right? So we know that P of t is equal to some initial amount times e to the kt, right? So we know P of t equals P naught times e to the kt. And we also know that P at 139 equals 1/2 P naught equals 1/2 of P naught, right? Right? Okay, so we can figure out exactly what's going on here. We can figure out exactly what happens, right? So P, P at 139 is P naught e to the, actually let me make this negative k, e to the negative k times 139. Right. So, so the question is basically figure out k. Figure out what k is. Okay. You say, okay, well, I know at the time 139, I got half of what I started off with. I know that time 139, that it's going to look like this: P naught e to the negative k times 139. And so you set those things equal to each other, right? You say, okay, 1/2 P naught equals P naught e to the negative 139k, right? And then you just solve, right? You get 1/2 equals e to the negative 139k. And so, taking the logs of both sides, you get negative 139k equals negative the natural log of 2. Right? So what's k? K is 139 over the natural log of 2. Okay. And so, if we want to describe the decay of polonium, what we see is that P of t is going to be your initial amount times e to the negative 139 over natural log of 2 times t. Right? So we have this equation that describes how polonium decays. So I think there's not much time. In fact, this is the end of class. So, okay. I think you should be able to do, so I sent out the assignment this morning for 7.5 and 7.7. You should all have it, I hope. But the last problem in 7.7 you cannot do. So don't do the last problem, because that relies on something we haven't talked about yet. Yeah. So don't do the last problem. But everything else should be possible, I think. Last problem. Okay, that's it. That's it. Thanks for coming. Good, I'm glad. Yeah, just don't do that again.